All around the world, countless people use electricity for almost everything. So, the electricity demand is expected to increase day by day. Nearly half of the increase will have to be met by burning fossil fuels. As the world raises concerns over reducing carbon emissions, renewable energy sources hold the key to combat climate changes. Among them, power generation using solar PV is on the rise. How do we harness solar power? Solar panels harness the energy from the sun and convert to electricity. They typically produce DC electricity. Inverter changes DC electricity to usable AC. To provide efficient power conversion at a reduced cost, highly efficient power conversion systems are required. For that, it is required to have optimal designs for the inverters and front-end converters. This is the proposed system for an efficient power conversion at a reduced cost. First, let's move on to the front-end DC to DC converters. In this design, we propose an advanced DC to DC converter as the front-end converter of the system. It is a 4-phase floating interleaved boost converter where the input voltage source is connected in series with the output capacitors. The same converter arrangement provides these advantages as well. To evaluate the input and output performance of the proposed converter, it was modeled in MATLAB Simulink. The input current ripple frequency has increased. Ripple percentage is less compared to conventional boost converters. Output voltage is capped at 750 volts and ripple is around 0.93%. Next, we have the maximum power point tracking technique. In the proposed system, P N N algorithm is used. To compute the maximum power point, it increments or decrements the operating voltage of the PV array and measures the instantaneous power output of the PV panel. To control the 3-phase VSI, current controlled mode, indirect current controlled method is used. DQ transformation methodology is used to convert sinusoidal quantities into DC quantities. This is the overall control block diagram of the inverter. These are the requirements for grid interconnection according to the applicable standards. The proposed system is modeled and simulated in MATLAB Simulink. The performance of the system is evaluated under varying irradiance. Power output of the system is almost same as the maximum power output of the PV array under varying irradiance. The inverter current output also changes with the irradiance. Power quality is a major concern in grid-connected inverters. Total harmonic distortion on the output current of the inverter was about 2.18%. To evaluate the inverter response to various voltage and frequency deviations, a monitoring unit was used. To conclude what we have done, we have developed a design of a source-to-grid complete interconnecting systems for solar PV applications having the following outcomes.